Welcome back to the channel. I'm so excited about today's video because we're taking a deep dive into one of the most fascinating topics in AI, neural language models. If you've ever wondered how we went from simple RNNs to the powerful language models we have today, like ChatGPT, Claude, and Gemini, this video is your complete roadmap. We'll break down RNNs, LSTMs, GRUs, and finally transformers. We'll talk about what problems each one solved and why the 2017 paper, "Attention is All You Need," literally changed everything. By the end of this video, you'll understand not just how these models work, but why they evolved the way they did. So let's jump right in. Before we talk about the models themselves, we need to understand a fundamental concept: why sequence matters in language. Language isn't just a bag of words thrown together randomly. The order matters tremendously. Look at these examples on screen. The dog chased the cat versus the cat chased the dog. Completely different meanings, same words, different order. And if we scramble them, like dog, the cat, the chased, it becomes nonsense, even though all the words are there. So for machines to truly understand language, they need models that can process information as ordered sequences, not as isolated, unrelated pieces. They need to understand context, dependencies, and relationships across the sentence. This is where sequence models come in, and it all started with RNNs. Enter recurrent neural networks, or RNNs, the original sequence model. The brilliant idea behind RNNs is simple but powerful. What if we create a neural network with a loop? What if the output from the previous step helps inform the current step? Look at this example. I love machine learning. Instead of processing each word independently, the RNN passes information forward. When it sees I, it creates a hidden state. When it sees love, it uses that hidden state from I to better understand love. Then machine uses context from both previous words, and so on. This was huge for early NLP. It enabled machine translation, text generation, and gave machines a form of memory. The math is actually quite elegant. You can see the formula here. The hidden state at time t depends on the previous hidden state and the current input. But there was a problem. Actually, a big problem. RNNs suffer from something called the vanishing and exploding gradient problem. In simple terms, as sequences get longer, the network struggles to remember information from earlier in the sequence. Imagine trying to remember the beginning of a very long sentence by the time you reach the end. The information just fades away. This made RNNs unreliable for longer texts. We needed something better. We needed a model that could remember selectively. In 1997, researchers introduced long short-term memory networks, or LSTMs, and they were a game changer. The key innovation? Gates. LSTMs introduced three types of gates that act like intelligent filters for information. First, the forget gate. It decides what information to throw away from the cell state. Do we need to remember this, or can we forget it? Second, the input gate. It decides what new information to store. Is this important enough to remember? Third, the output gate. It decides what to output based on the cell state. What should we pass to the next step? These gates work together to create selective memory. LSTMs can remember important information over hundreds of time steps, something RNNs could never do reliably. In PyTorch, using an LSTM is actually quite straightforward. You can see the implementation here. Notice we get both a hidden state and a cell state. That cell state is the long-term memory. LSTMs became the go-to for speech recognition, sentiment analysis, machine translation, anywhere you needed to remember long-range dependencies. But they weren't perfect. LSTMs are computationally expensive. Lots of parameters, lots of calculations, and they still process sequences one step at a time, which means you can't parallelize the computation efficiently. This brings us to GRUs. Gated recurrent units, or GRUs, are like LSTM's younger, simpler sibling. Researchers asked, do really need 3 separate gates? Can we simplify this? And they did. GRUs combine the forget and input gates into a single update gate, and they have a reset gate that controls how much past information to forget. The result? Fewer parameters, faster training, and often comparable accuracy to LSTMs. The implementation is cleaner too. Notice we only get one hidden state, not separate hidden and cell states. GRUs became popular when you needed faster convergence or had limited computational resources. They're still widely used today for speech recognition and certain NLP tasks. But here's the thing. Both LSTMs and GRUs still have that fundamental limitation. They process sequences step by step. You can't easily parallelize them, and very long sequences are still challenging. We needed a completely different approach. We needed to think about sequences in a fundamentally new way. And in 2017, that's exactly what happened. 2017, the paper that changed everything. Attention is all you need. This wasn't just an improvement. This was a paradigm shift. RNNs, LSTMs, GRUs, they all process sequences like this. One word, then the next word, then the next word. Sequential, step by step. Transformers said, what if we analyze all words simultaneously? What if every word can look at every other word at the same time? This is the self-attention mechanism. Let me explain what this means. Look at this sentence. The animal didn't cross the street because it was too tired. What does it refer to? A human knows it refers to animal, not street. We understand this because we can attend to different parts of the sentence simultaneously. Transformers do the same thing. Through self-attention, the word it can attend strongly to animal and weakly to other words, learning the reference relationship. The math behind attention is elegant. You create query, key, and value matrices, compute similarity scores, and then take a weighted sum. Don't worry if the math seems complex. The key insight is that every word interacts with every other word. And here's the kicker. Because all words are processed simultaneously, you can parallelize everything. This means training on GPUs becomes incredibly efficient. Multiple attention heads let the model capture different types of relationships, syntax, semantics, long-range dependencies all at once. The impact of transformers cannot be overstated. BERT revolutionized understanding tasks like question answering and search. GPT, the foundation for ChatGPT, mastering text generation. T5, a unified framework for any text-to-text task. And today's models, Claude, Gemini, Llama, all built on transformer architecture. Transformers didn't just improve existing tasks, they enabled entirely new applications. Machine translation that actually sounds natural. Chatbots that can hold coherent conversations, code generation that helps developers, multimodal models that understand images and text together. And the best part, thanks to libraries like Hugging Face, using these powerful models is incredibly accessible. Just a few lines of code and you're using state-of-the-art language understanding. Now, let's put everything together and compare these models side by side. All 4 can handle sequences. That's their core purpose. But long-term memory. RNNs fail here. LSTMs, GRUs, and transformers all succeed, but in different ways. Here's a crucial difference. Parallelism. RNNs, LSTMs, and GRUs must process sequentially. Transformers can process everything at once. This is huge for training speed and scalability. Training speed reflects this. LSTMs are slow because of their complexity and sequential nature. Transformers are fast when you have lots of data and powerful GPUs. And scalability. This is why we have billion-parameter models today. Transformers scale beautifully. You can't build GPT-4 with LSTMs. The architecture just doesn't allow it. Use cases tell the story. RNNs for early experiments, LSTMs and GRUs are still used in specialized domains like time series or speech, but transformers dominate modern NLP entirely.
So why did transformers completely take over? Let me break it down. Number 1, they solved the vanishing gradient problem. With direct connections between all positions through attention, information flows freely across long distances. Number 2, Massive parallelism. Training transformers on modern GPUs is incredibly efficient. What would take weeks with LSTMs takes days with transformers. Number 3, scalability. Want a bigger, more powerful model? Just add more layers, more attention heads, more parameters. Transformers scale gracefully. Number 4, better performance. On virtually every benchmark, translation, summarization, question answering, transformers dominate. Look at the real-world impact. Google Translate got dramatically better almost overnight when they switched to transformers. ChatGPT, GitHub Copilot, advanced search engines, all transformers. Even multimodal models like GPT-4 Vision and DALL-E use transformer-based architectures. The revolution was complete. So where are we now and where are we going? We're firmly in the era of large language models, LLMs, and they're almost exclusively built on transformer architectures. But research hasn't stopped. In fact, it's accelerating. Efficiency is huge right now. Can we make smaller models that perform as well as larger ones? Techniques like distillation and pruning are making this possible. Alignment. Making sure AI is helpful, harmless, and honest. This is critical as these models become more powerful. Contextual memory. Models that can handle 100,000 tokens or more in their context window. Imagine analyzing an entire book at once. Multimodality, seamlessly combining text, images, audio, and video. The future isn't just language models, it's intelligence models. And look at how far we've come, from LSTM in 1997 to transformers in 2017 to billion-parameter models just a few years later. Understanding this history isn't just academic. It gives you a roadmap. It helps you understand the trade-offs, choose the right tool for your problem, and anticipate where the field is heading next. Now, for those of you who want to get hands-on, and I really encourage this, let me show you some practical implementations. Here's a simple RNN for text classification. The structure is straightforward: embedding layer, RNN layer, fully connected layer for classification. LSTM for sentiment analysis. Notice the bidirectional flag. This means we process the sequence forward and backward, capturing context from both directions. This typically improves performance. GRU for language modeling with a generation function. This shows how you can use these models auto-regressively, predicting one token at a time to generate text. And finally, using a pre-trained transformer model. This is the power of modern NLP. You don't need to train from scratch. Fine-tune BERT or GPT on your specific task with just a small amount of code. I encourage you to try these examples, modify them, break them, understand how they work. There's no substitute for hands-on experience. Let me dive a bit deeper into self-attention, because it's really the core innovation of transformers. Think of it like a database lookup. Query is what am I looking for? Key is what do I contain? And value is what do I actually output? We compute similarity scores between queries and keys. How related are these words? Then we apply softmax to get attention weights, a probability distribution. Finally, we use those weights to combine the values. The implementation shows this clearly. Notice we do this with multiple heads, typically 8 or 16. Each head can learn to attend to different types of relationships. One head might focus on syntax, subject-verb relationships, another on semantics, related concepts, another on long-range dependencies, pronouns to their antecedents. Together, they create a rich, nuanced understanding of the text. Let's talk numbers for a moment. Complexity analysis. RNNs and LSTMs are O of n in time complexity, linear with sequence length. That's good, but they're not parallelizable. Transformers are O of n squared, quadratic with sequence length. That sounds worse, right? But here's why it's actually better in practice. Full parallelization. Even though there are more operations, you can do them all at the same time on a GPU. It's like having one person do 100 tasks sequentially versus having 100 people do them simultaneously. More total work, but much faster completion. The real-world result? Transformers often train faster despite higher computational complexity, and they scale to much larger data sets and model sizes. That said, there's active research on efficient transformers, reducing that O of n squared complexity for extremely long sequences. Flash attention, sparse attention patterns, these are making transformers even more efficient. All right, let's bring it all home. We've covered the entire evolution of neural language models. RNNs pioneered sequential processing, but couldn't handle long-term dependencies reliably. LSTMs introduced gates to solve the memory problem, selective forgetting and remembering. GRUs simplified the architecture with fewer parameters but similar performance. And transformers revolutionized everything with self-attention, enabling parallelism, scalability, and the LLM era we're in today. 2017 was the turning point. Attention is all you need wasn't just a paper. It was a paradigm shift that enabled ChatGPT, Claude, and every modern AI assistant you interact with. Here's what you should remember. Understand the history. Know why each innovation happened. Build practical skills. Learn to implement and fine-tune these models. Stay current. The field moves fast. Follow the latest research. Apply your knowledge. Build projects, experiment, learn by doing. Whether you're a student, a developer, or just an AI enthusiast, understanding these fundamentals give you a solid foundation to build on. If you found this video helpful, please hit that like button. It really helps the algorithm show this to more people. Subscribe if you haven't already, and click the bell so you don't miss the next video. Thanks so much for watching, and I'll see you in the next one.